Good afternoon, everyone. My name is Jian. It's my pleasure to be here to introduce ShiftLock, a work done in collaboration by me and my colleagues from Tsinghua University. As part of the hardware assist session, this work focuses on leveraging hardware features of RDMA to accelerate distributed lock protocols. So I guess I will first need to give a brief introduction to the RDMA technology, because our paper is the only one that in this conference that has RDMA in the title. So RDMA means remote direct memory access. It is a user space networking technology that allows you to directly access remote memory while sidestepping remote CPUs. Without CPU intervention, RDMA becomes blazingly fast. A network round trip can be finished within 2 microseconds. So RDMA requests are called verbs. They are one-sided verbs that will sidestep remote CPUs, including read, write, and atomics. Also, there are conventional two-sided verbs, including send and receive, that still require CPU assistance. So why are we doing research in RDMA? Because RDMA hardware is evolving rapidly, and recent products provide many fantastic opportunities. In this work, we mainly focus on the rich semantics of the verbs they provide. Specifically, RDMA atomic verbs can operate on larger than 8-byte values while providing bit mask semantics that allow you to modify an arbitrary part of the operand while keeping the remaining parts intact. So I guess it is safe to say that RDMA atomics are much more powerful than their CPU counterparts. This fact drives us to develop new distributed protocols with the help of RDMA, for example, lock protocols. In RDMA locks, clients directly read and write log entries stored on the server. They coordinate with each other as if in a single machine, except they access the memory with RDMA verbs. This scenario is also called a one-sided lock because only client CPUs are active, while server CPUs just do nothing. Compared to traditional locks, RDMA locks are good because they benefit from RDMA's advantages, including microsecond level latency, very high throughput, and low CPU usage. But everything has two sides. Because the server is inactive, clients do not get any feedback when they fail to acquire lock, and they must retry. The RDMA NIC is not that good at handling so many concurrent retries, especially when they have conflicts. As a result, if there is high contention, you may expect a significant performance drop of RDMA locks. If we have 200 contending clients, they will cut the throughput by about 95%. The ultimate problem here is that there are too many retries coming from clients that relentlessly try to acquire a lock that was occupied by others. These retries will devour the server's IOPS resources and cause performance degradation. With a typical compare and swap implementation, more than 85% of the retries will fail in a highly contended scenario. Good news, this is not a new problem. A solution is to let clients queue up and hand over locks, which is an existing idea in the well-known MCS and CLH locks. Handover means that a client directly gives the lock to another client via peer-to-peer messaging without involving the server. With handover, clients can just wait locally for the receipt of the lock instead of performing retries. Bad news, we find that very few RDMA locks adopt this idea, although it is already 34 years old. What's the problem here? Well, in fact, there are some challenges that make it a bit hard to implement the MCS lock in the RDMA network. First, RDMA control path is very slow compared to its data path. It takes milliseconds to configure a new connection between two clients. This results in a dilemma. If we want to connect all clients beforehand, it will be unscalable, but if we don't, it will be slow. Second, RDMA is much more slower, about 20 times slower than local memory accesses. This makes it hard to add useful features such as reader-writer semantics to the MCS lock. If you look at existing reader-writer variants of the MCS lock, you will notice that they need to touch the lock for multiple times to acquire or release it. This will translate into multiple network round trips and add higher latencies in the context of RDMA. Finally, MCS lock assumes that clients will never die, but this is not the truth in a distributed system. There are two questions to answer. First, how to detect a failure. Second, how to correctly recover from it. To address these issues, we developed ShiftLock. It adopts the idea of MCS lock while introducing several key designs, including scalable client-to-client communication, single round-trip reader-writer protocol, and fault tolerance mechanism. To begin with, we first take a quick look at the MCS lock protocol itself. The principle of MCS is to organize clients in a queue. The lock entry is a pointer to the queue tail. To acquire a lock, a client simply appends itself to the tail. If it is also the queue head, for example, the client A here, it can happily acquire the lock. Otherwise, for example, client B here, it will have a predecessor in the queue, that is A. B writes to the memory of A to update its successor information, and then waits until A hands over the lock to it by updating a flag in its memory. Now we start to introduce our contribution. First, we discuss how to implement client-to-client communication required by MCS lock in an RDMA network. In a distributed scenario, clients will run on different nodes. They must communicate via RDMA, and we need to choose proper verbs for them and solve scalability issues. MCS lock wants client to write to each other's memory, but to perform a write over RDMA, we need a large amount of metadata, which must be embedded in the lock entry as a part of a remote pointer to a client. To save space, we point out that since the ultimate goal of client-to-client communication is to send a message that will eventually be processed by remote CPU, we can use two-sided send verbs instead of the one-sided writes to perform such communication. Sends have similar performance with writes as long as the opponent is ready to receive. Also, these sends are not RPC calls, and clients do not need to spare CPUs to monitor them all the time. Instead, they handle these received messages only when needed. For scalability issues, since it's unscalable to maintain conventional connections, we turn to use RDMA dynamic connections instead. Dynamic connection allows a client to connect to different remote endpoints on a data path. It is very fast. The reconnection overhead is less than 1 microsecond. And as we have said before, client's route information is embedded in the lock entry as part of the queue tail pointer, so others can use that information to dynamically connect to that client. Second, we introduced ShiftLock's reader-writer lock protocol. Previously, we are assuming that only writers exist, and the lock is a mutex. When they are readers, we must find a way to maintain them and transfer the lock ownership between readers and writers to avoid bad things such as starvation. Due to the high networking latency, mixing all clients in the same queue is definitely not a good idea. Instead, we only maintain writers in the queue and use 3 new fields in the lock entry to maintain readers. First, we use a counter to count active readers that are trying to acquire or actively holding the lock. Thus, clients can detect whether readers or writers exist and acquire the lock if there are no conflicts. The remaining 2 fields are to solve the case when there are conflicts. To help a writer acquire the lock when readers are holding it, we introduce the second field, a lock release counter. Clients increment this counter whenever they release the lock. Now let's consider a writer at the queue head. When it appends itself to the queue tail, it will also atomically read the entire lock entry. It will then know how many readers are holding the lock before it, and can spin on the lock release counter until it becomes a value that signals all previous readers have left. And this value is simply the sum of the reader counter and the release counter. The third field, epoch, helps reader acquire the lock when a reader is holding it. To explain the meaning of this name, we know that the entire lifetime of a queue-based reader-writer lock can be divided into many epochs, with each epoch consisting of 3 steps. First, 0 or more readers acquire and release locks. Second, a writer appears and takes the lock. Third, writers hand over the lock in the queue. Now, it becomes obvious that giving the lock to readers is equivalent to starting a new epoch. As a result, when a writer is holding the lock, we let readers spin weight on the epoch field. When the writer releases the lock, it also atomically reads the number of readers and the release counter. And it changes the current epoch to pass the lock to readers. Now the situation for the next writer is similar to what we have discussed before. The current writer can do some calculation and send a message to the next writer, asking it to spin wait on the release counter until all previous readers have left. In this design, the signal for readers to acquire is the change of the epoch, not its absolute value. The epoch is not like a mode, but it's like a clock in digital circuits. It guarantees single round-trip lock acquisition without contention because clients can acquire in any epoch. Also, to avoid reader starvation, readers must proactively transfer the lock to readers. We set the transfer criterion as the number of consecutive handovers. If it reaches a threshold, which is 16 in our implementation, the lock will be given to readers. Finally, we discussed how ShiftLock tolerates failures. We focus on client failures because if the server fails, the only choice is to let all clients switch to the new server and retry from the beginning. Although ShiftLock introduces lock handover among clients, it adds no extra complexity in failure detection. If a client fails, then eventually all clients will be blocked and no one will release the lock. The release counter will stop changing. So we can adopt the idea of leasing and detect a failure if the release counter keeps unchanged for a certain period of time. When the release counter is unchanged for decades, clients can detect the failure. However, it is the server that is responsible for performing the recovery. Specifically, the server maintains an era, which counts how many recoveries have occurred. The client that detects the failure asks the server for recovery in the current era. The server will bump the release counter for a very large value, clear all other fields in the log entry, and increment the era. The leap of the release counter will make other clients aware of this recovery, so they can retry acquiring the lock. This design effectively prevents clients from performing outdated recoveries that would otherwise be possible due to the ABA problem for a small chance, which will cause the system to explode. Now we have finished with the major design points of ShiftLock. In summary, it achieves scalable and efficient client-to-client communication with two-sided verbs and RDMA dynamic connection. It develops a low-latency reader-writer lock protocol that guarantees single round-trip acquire and release if without contention. Also, it provides fault tolerance. Please see our paper for more technical details. We have implemented ShiftLock in around 7,000 lines of Rust code and compared it to some existing RDMA locks in a testbed of 6 nodes. Overall, ShiftLock, the dark blue line in the figures, delivers the highest performance. It improves the throughput and latencies for reader-writer locks at different scales. However, compared to a mutex, some writers might wait longer in ShiftLock because, as we have discussed before, writers need to proactively give the lock to readers to avoid starvation. This can result in somewhat higher tail latencies. By picking the hardware counters, we find that the reason behind ShiftLock's performance advantage is that it effectively reduces retries and has the lowest pressure to the server-side RDMA NIC. A factor analysis on the cast lock shows impressive effects of the backup strategy, which is a conventional mechanism to reduce the number of retries, but also proves that it can only partially alleviate the problem instead of solving it entirely. ShiftLock's advantages do come with some overheads. In terms of recovery, with the same least time, clients must wait longer than existing RDMA locks to be sure of a previous failure. This is because ShiftLock allows clients to hand over locks, so we must consider the time spent in handover. As a result, its recovery performance is slightly lower than previous work, but they are still similar. To save time, we only show major performance results here, and please see our paper for more detailed analysis. This concludes my talk today. If you are interested in our work, please feel free to raise any questions or try our artifact. Thank you very much.